Okay, guys, so this will be the first of a couple of lectures that will make up for the classes that we're going to miss, and should also put us just about back on schedule since we were slightly behind anyway. What I've done is instead of doing 50-minute lectures, which sort of are a bit of a mouthful, I'll just do a couple 30-minute lectures that should be a bit more palatable, I guess. All right, so we'll be looking again at acids and bases. And if you remember, last day we defined an acid in several different ways. We used the Arrhenius definition, which basically said that an acid was a compound that would dissolve in water, giving rise to H plus ions, whereas a base would dissolve in water to give rise to hydroxide. We saw that definition was rather poor because on one hand, it would limit the acid-base phenomenon to an aqueous medium, and also the currency for acids and bases were different. One made protons, one made hydroxide. The Bronsted-Lowry was an advantage over that one because it said an acid was simply a proton donor and a base was a proton acceptor. And in that case, we didn't limit the acid-base phenomenon to any medium, and we normalized the currency for the acid-base phenomenon. So an advance over that was the Lewis definition, which basically holds that an acid is an electron pair acceptor, a base is an electron pair donor, and that has the advantage of considering the acid-base phenomenon as a chemical phenomenon, because chemistry is fundamentally about the transfer of electrons. So an acid-base reaction then is fundamentally an electron transfer reaction, where the base donates an electron pair to the acid, which accepts the electron pair. We also saw that we could use the term acid and electrophile almost interchangeably because they were both species that would accept electron pairs. And we could use the term base and nucleophile almost interchangeably because they were both species that would donate electron pairs. I did mention in lecture that there's a slight subtle difference between a base and a nucleophile. And I sort of alluded to the fact that, acidity and basicity are equilibrium phenomena, and they're defined by the delta H of a reaction, so the position of equilibrium. Whereas nucleophilicity, electrophilicity is more of a kinetic phenomenon. It's more of a rate deal. But we'll talk about it in some more detail later on. It's not something for us to be too concerned about now. So we said that a strong acid HA would ionize a lot to give rise to, of course, H plus and A minus, for which I can write an equilibrium constant, which is a conc of H plus times the conc of A minus over the conc of HA, so that a strong acid would be associated with a large Ka value and also a small pKa value, because the pKa is the negative log. The pKa is the negative log. Well, the pKa is the negative log to the base 10 of the Ka value. And I gave an example last day that showed that the minus sign causes the direction to be inverted. So a strong acid, which has a large Ka, will have a small pKa. And similarly, a weak acid, let's say Hb, which is defined as one that is poorly ionized, to give B plus, B minus, and H plus, this will have a small Ka value, obviously because the concentrations of the products are small. And if you multiply two small numbers, you get an even smaller number, and you're dividing it by a big number. So the Ka value is going to be small. And what you find then is that for a weak acid, it's going to be associated with a small Ka value, but also with a large Ka value. And I said that it becomes very easy if I gave you a list of acids and I said, well, rank the following acids in terms of decreasing strength. You will simply look at the Ka values or the pK values, whichever ones you're given, and you can make an assessment based upon those values. The trick comes in when you are asked to assign the strengths of acids, relative strengths of acids, and you have not been given data tables. So you will have to then fall back on your understanding of what makes an acid strong. In other words, what are the factors that affect acid strength. So the factors affecting acid strength. And we said that those factors were, one, the HX bond, or the HA bond, doesn't really matter. Okay, and we looked at this in terms of both the length of the bond, which of course is also these are the strength of the bond, and we also looked at the polarity of the bond. And in polarity, we're looking both at the degree of polarity, right? That was how polar is the bond, and also the direction of polarity. Right? In other words, where does the delta plus charge lie? Two, we looked at X minus, or if you will, just X, I guess. Excuse me. I'm sorry, excuse me. We looked at X. We looked at the size of X, the electronegativity of X, and we looked at the hybridization state of X. And then the third factor, which is the one we looked at actually first, was the solvent. And we did the solvent. We said that, you know, we saw the example that if I were to bubble HCl into, say, hexane that had litmus in it, then there was no color change. It would remain blue, and that's the HCl would dissolve in the hexane, but it does not ionize, because the hexane is a nonpolar solvent, and therefore does not form strong enough bonds to break the HCl bond. It doesn't form strong enough bonds with the HCl to break those bonds, and then even if it were to do so, it wouldn't stabilize the ion pair that's generated. Whereas if I were to bubble HCl into ethanol that had litmus in it, I would get the litmus going from blue to red, because the ethanol not only would, in fact, let me just run that through. Not only would the ethanol, right, in fact, I'll just use a generic symbol here for the solvent. The solvent, if the solvent is polar, right, will bond to the HCl. This is delta plus, this is delta minus. A polar solvent will bond to the HCl via dipole-dipole bonds. And in so doing, these bonds are forces of attraction. So literally, this polar end, and of course you're going to have several molecules of solvent on this side, and several molecules of solvent on that side. And together, what these molecules will do is they will form bonds with one end of the molecule, form bonds with the other end of the molecule, and literally pull the HCl bond apart, right? And you can do that if the molecule is polar. So you're going to have, you know, strong dipole-dipole interaction. And then once the bond is broken and the ions are released, then the solvent molecules sort of greedily surround each ion, and you form the solvated ion. So the solvent allows, a polar solvent allows the acid to express its acidity, which basically is a tongue-in-cheek way of saying it's going to cause it to ionize, and once it's H+, then we can see evidence of acidity, vis-a-vis litmus turning from blue to red. Then we looked at the nature of the HX bond, and we finished that last day as well. We said that, you know, really what I want for something to be an acid, fundamentally, is for the HX bond, or the HA bond in this case, to break. Right, and let's keep the letters consistent. Let's make it HX. All right, what I want fundamentally for an acid is for the HX bond to cleave. Right, so I'm going to end up with H plus and X minus. And obviously, the longer this bond is, the weaker it is. The weaker the bond, less energy is required to break it. And also, more of the bonds will break under given conditions. So if the bond is long, then the bond is strong. If the bond is long, then the bond is weak. If the bond is weak, then it is easily broken, which really has nothing to do with acidity, because that's a kinetic issue. But if the bond is weak, it means that a small amount of energy can break a lot of those bonds. And therefore, the extent of bond breakage will be large, and the acid will be strong. We saw that what we really want is for the bond to be polarized in such a fashion that the H has a delta plus charge on it, which of course means that X will be delta minus. And what I really therefore want is for the H to be more protonic. So I want my H to look protonic, right, have a significant positive charge. and I want the polarity to be such that the H is delta plus, and the more delta plus the H is, the more acidic is the compound, by and large. We did make the point yesterday as well that you have to be careful when you compare hydrides. So if I compare hydrides, for example, across a period, so I look at, say, methane versus ammonia versus water versus HF, that my acidity increases in this direction. I have increasing acidity. And what happens here is that the two factors that are in diametric opposition. This is a very nice term that you guys might want to put in your arsenal. We say things are diametrically opposed, or the factors are in diametric opposition. And basically what it means is that if I look at the changes as I go from carbon to N to O to F, there are two things that are happening, and they're related. One is that the atom is getting slightly smaller. So I'm going from this for carbon to this for nitrogen to this for oxygen to this for fluorine. Well, that's a bit small. Maybe this for oxygen and that for fluorine. So there is a gradual decrease in the size, but it's not a massive decrease in size. So size gets smaller going across the period, but not very much smaller. On the other hand, the electronegativity changes markedly because carbon has the same electronegativity as H, which is very, very low, but F is the world's most electronegative element. And then I made the point last day that when you go across a period, you're going from metal, which is strongly electropositive, to non-metal, which is strongly electronegative. Whereas if I go down any group, if I'm a metal at the top, like say the group 1s, if I'm lithium at the top, I come down to cesium at the bottom, I'm still a metal. Or if I'm fluorine at the top and I come down to astatine, I'm still a non-metal at the bottom. And so your electronegativity does not change much going down a group, but it changes dramatically across a period. So in other words, the change in electronegativity, right, the change in electronegativity going across a period is much, much bigger than the change in size. And therefore, going across a period, electronegativity is a dominant argument. Right? So going across a period, even though the HX bond gets slightly shorter and therefore slightly stronger, that factor pales in comparison to the fact that the H is getting significantly more protonic. And therefore, going across a period, electronegativity wins. On the other hand, if I'm going down a group, so I'm considering HF, HCl, HBr, and HI, well, here, the change in size is much greater than the change in electronegativity. So going down a group, so this is for a period, right? But going down a group, the change in size, right? Change in size is much, much greater than the change in electronegativity. So size is a dominant argument. And therefore, even though the H here is by far the most positive, right? Even though the H is more positive in HF than it is in HI, so the H is more protonic, the point is the bond is shorter here, much, much shorter than it is in HI, right? And size being the bigger factor, it means that the length of the bond is a dominant issue. The longer bond is going to give rise to a stronger acid. So when we're comparing hydrides across a period, in other words, periodic partners, we look at atomic size. When we're comparing hydrides down a group, in other words, group partners, we look at the change in, I'm sorry, I'm not sure what I said. When we're going across a period, we look at change in electronegativity. So electronegativity is a dominant argument. When we go down a group and we look at periodic group partners, we should look at the change in size. So across the period, we look at electronegativity. Although we will mention that there is an issue with size, but it's less important. When we're going down a group, we look at size, although we will mention that there's an electronegativity issue, but that's less important. So that size and electronegativity are diametrically opposed. Okay? All right, so if we go back, right, we were looking at the factors that affect the strength of an acid. So we've looked then at solvent and at the nature of the HX bond. The other factors are size, electronegativity of X, and hybridization of X. And you can pretty much, I think, see where this is going. Because it has a bearing on the HX bond. So obviously, if the atom, if I compare, say, fluoride, or let's compare fluorine against iodine. And I'm going to ask the question, well, for which of these hydrides will the acid be stronger? In other words, will HF be stronger or weaker than HI? Well, one fact I'm going to look at is the size of those two atoms. And how is that important? Well, the size of the atom plays a role in two ways. One, it affects the length of the bond, right? The length and therefore the strength of the bond. And we've already argued how that operates. So if we're looking at I and F, which are group partners, because iodine is bigger than fluorine, much more so, the bond is going to be longer, it's going to be weaker, it'll be broken more completely, which gives rise to HI being the stronger acid. But size has another component which deals with something called, we mentioned this before, the charge density on the ion. So imagine then, let's say this is fluorine, which has a minus charge in it because the H plus ion has come off. So HF has broken up to give me F minus. Similarly, HI has ionized to give rise to the H plus ion and the I minus ion. Now, both the F minus and the I minus have a charge of 1 minus. But in the fluoride, the charge density, which is the charge, good Lord, which is the charge over the area, right? So charge density, right, is the charge over the area, all right? The charge density is a measure of the intensity of the charge. How intense is the force field around the ion? The charge density in the fluoride ion is huge, whereas because the iodine is a much bigger atom, the minus charge is dispersed or dissipated or delocalized over a much larger surface area. So we say here that the I minus charge, the 1 minus charge, is dissipated, okay, or it is delocalized. Delocalized. Oh, good Lord. Okay, it is dissipated or it is delocalized. In other words, it's evenly spread. And obviously, if I'm trying to carry 100-pound weight, it's much easier to carry the 100 pounds, on my back than to carry it on the tip of my finger. It's the same 100 pounds, but it's more bearable if I spread the weight around than if I were to try to concentrate it. So it means then that F minus is really an intensely charged species, and that makes it unstable. So what will F minus do? And the answer is it doesn't like being F minus. So what it'll do is it'll gobble up the proton that's formed with it to cloak itself. So in other words, what will happen is HF, let's say HF does this to give rise to H plus and F minus. The F minus, which is a very unstable species because of the high charge density, will be very unstable and will try to cloak itself in a proton, gobble up the proton, and hide as HF. Because as HF, the F is not quite as unstable as it is as F minus. In other words, the tendency of F minus to return into HF is great compared to the tendency of HF to ionize to form HF. So what this means then is my Ka value is going to be low. On the other hand, Hi will ionize. The bond is long, the bond is weak, so it's going to ionize pretty well and give rise to H plus and I minus. But I minus is a big species. So yeah, it's got a minus charge on it. It's got a minus charge on it just like the F. But for heaven's sake, the minus charge is dissipated, delocalized over a much larger surface area. So the charge density is very, very small. So the I minus is not desperate to cloak itself in a negative charge, in a positive charge. It's not desperate to cloak itself in the proton. And so really, it just has very little interest in the proton. So the tendency of I minus to gobble up the proton and go back into Hi is really very little. So the net effect is that the Ka value for Hi is very, very high. So the size of I, or the size of the atom to which H is bound, affects the acidity of the compound in two ways. One is in terms of the length and strength of the bond. So if you will, that affects this arrow, right? Because obviously the longer the bond, the more easily and more completely, which is the point, the more completely it breaks. The other factor is that the size of the atom affects the charge density on the ion. And the larger the atom, the lower the charge density, the less unstable is the anion, the less desperate it is to cloak itself from a proton, and therefore the less interest it has in the proton. So the return tendency, the return arrow, is very, very small, and therefore the acid is going to be large. Okay? So, which again really sort of, bears out the fact that as you go down a group, what is a great change in size, the strength of the acid rises dramatically. Okay, so we've done the size of the atom. Let's look at the electronegativity of the atom and see what role that plays. Well, as you might expect, right? What I want is for the electron pair in the HX bond, right, to come onto X minus. So obviously, the more electronegative X is, the closer to X will the electron pair lie. So if I were to look at, say, a CH bond and an FH bond, the electron pair in a CH bond lies bang smack in the middle. The electron pair in an FH bond lies very close to the F. The consequence is there is no dipole on the H. This H is not protonic. Here, there is a significant dipole. This H is very protonic. And all things being equal, for example, if size is very, very similar, as it is going across a period, then this would be the stronger acid because electronegativity is a dominant argument. Now, what does that mean? Suppose I looked at these three species. I looked at hydroxide, I look at water, and I look at H3O+. If I were to ask you which of these species is the strongest acid, or in fact even I can go to H4O 2+. And if I ask you which one of these is the strongest acid, well, what would you tell me? Well, the factors affecting the strength of an acid are the solvent, and unless you're told otherwise, you assume the solvent is the same, so that's not a factor. 2 is the HX bond. Okay? Well, in this case, X is O. So the HX bond I'd expect to be pretty much the same. So the lengths and strengths will be the same, or the polarities I'd expect to be different, somewhat different, because really I'm looking at an electronegativity issue. Because the electronegativity of the atom and the polarity of the bond are related. And that really is where the answer falls. And of course, hybridization is a non-issue because all the O's are sp3 hybridized. So the answer really then comes down to what is the size of the dipole on this H? So yes, O is electronegative. But the ability of the O in hydroxide to draw the electron pair in the OH bond towards itself has to be compromised by the fact that the O is already negative. So if the O is already negative, then it's not going to be able to draw much more electron density towards itself. So this H will have a slight dipole, right? But nothing too great. This O is not negative. It has a smaller concentration of electron density, only 2 lone pairs compared to 3, and therefore it's more electronegative than that O, which means this H is more protonic. Obviously, with a positive charge on the O, I have now hyped up its electronegativity. I also have the O having only 1 lone pair. So its electron demand, its need for electron density has gone up. This H is even more protonic still. And obviously this H would be the most protonic of the lot, and therefore I'd expect acidity to increase in this way. Right, so I have increasing acidity or increasing Ka value. Okay? The last factor affecting the strength of an acid is the hybridization state. And we've actually seen this one already. So, for example, we know already if I looked at a terminal alkyne, that they are stronger acids than terminal alkenes, or than alkenes in general, which are stronger acids than alkanes. And the reason was that this carbon is sp3 hybridized, this carbon is sp2 hybridized, this carbon is sp hybridized. And as you remember, as the s character of the carbon-based orbital increases, which it does going this way, right? This is 50% s, this is 33 1/3% s, and this is only 25% s. What happens is two things. So here is my sp3 hybridized orbital bonding with the H. Here is my sp2 hybridized orbital bonding with the H. Here is my sp hybridized orbital bonding with the H. So what's happened is, for one thing, the bond has gotten shorter. And I would say, well, if the bond has gotten shorter, maybe the acid should get weaker, because the bond is, if it's shorter, it's stronger, right? And therefore it doesn't break quite as completely. But the size of the atom, I mean, we're looking functionally at carbon here, so the change in size is really very small. But the ability of carbon to draw the electron pair towards itself is increasing as I go this way. Because here the electron pair is far, here it's closer, here it's closer still. So since the electronegativity of carbon is increasing with increasing s character, the CH bond gets increasingly polar. So the H here is more protonic than is the H here, than is the H there. And as a result, the alkyne is a stronger acid than the alkene, which is a stronger acid than the alkyne. You know, I could look at something similar if I would look, for example, at a series of compounds of this type. If I look at a nitrilium ion, where the N is sp hybridized, if I look at an imine, where the N is sp2 hybridized, and I look at an amine, where the N is sp3 hybridized, I say exactly the same thing, that the amine is less acidic than the imine, right? And the nitrilium ion is actually way more acidic. Now, in this case, we're cheating a bit, because in addition to the increasing S character, and therefore the increasing electronegativity as I go this way, which was gradual for alkane to alkene to alkyne, there'll be an increase here, which is parallel to the increase above, but there'll be a massive increase in electronegativity between these two. Because not only have I gone from being sp2 to being sp, but I've also made the side positive. So I've souped up the electronegativity of the N. And therefore there'll be a significant jump in acidity going from the imine to the nitrilium ion. In other words, this gap between these is bigger than it is here. Okay. There's one other feature of the hybridization state that's important. And that is, let's imagine the orbitals again. So here is the sp3 hybrid of the carbon, of the alkene. Here is the sp2 hybrid, it's rounder and smaller. Here's the sp2 hybrid of the alkene. And here's the sp hybrid, round and small, of the alkane. We've seen that the hybrid size affects the electronegativity of the carbon. In other words, the proximity of the electron pair to the carbon's nucleus, which really is electronegativity. So it becomes increasingly electronegative, and therefore the CH bond becomes increasingly polar, the compound becomes increasingly acidic. There is another factor, and the other factor is this. Let's assume that the CH bond were to break, and I were to make the anion. So if I make the anion, my minus charge would be here, here, and here. Well, if I look at it, this negative charge, right, and in fact what I'll do instead, I'll draw the negative charge for the lone pair. So I'm going to put my lone pair of electrons where the swell of the electron density is, here, here, and here. So what this means is that in the anion, for the alkane, the minus charge is actually further away from the carbon nucleus than it is in the case of the anion from the alkene. Oh, sorry, that's my timer, so half an hour is gone, so I'm almost finished. So the lone pair of electrons in the alkane is further from the carbon nucleus than it is in the case of the anion from the alkene, than it is in the case of the anion from the alkyne, right? Because that's what we said, right? The H would have been here, here, and here. We pluck the H off. The swell is where the electron density is concentrated. So what this means then is that the electron pair on for the alkyne, for the acetylide ion, right? This is RC triple bond C minus. It's called an acetylide ion. That electron pair is very close to the carbon nucleus, whereas it is further away in the case of the alkanide ion. Right? So in the case of RC minus, this is the alkanide. Oh, crikey. This is the alkanide. The alkanide, or sometimes people call it the alkyde ion. Right? So why is that important? It's important because if you remember your basic Gen Chem, when I'm filling electrons into the orbitals, I have the 1s, then there's a gap to the 2s, then there's a gap to the 2p, right? Why is it that the 1s orbital is the most stable? And the answer is because it's lowest in energy. Why is that? And the answer is my nucleus is here. So as I move in this direction, I'm moving away from the nucleus of the atom, which means the electrons that occupy orbitals higher and higher and higher get more and more and more energetic. I'm going to turn that around. The most stable electrons are the ones that are housed in the 1s orbital. And why is that? Because they are closest to the nucleus. So the force of attraction between the electrons and the nucleus depends, as it always does, inversely upon r squared, where r is the distance between the nucleus and those electrons. So the closer the electrons are to the nucleus, the stronger is the force of attraction, therefore the more stable are those electrons. Okay? So electronic stability is defined in terms of proximity to the nucleus. So obviously, the C minus formed in the case of the terminal alkyne, in other words the acetylide, would be the most stable of all of the anions. And therefore, when HX is going to, I'll just do it here then, if HX is going to ionize, right, to form H plus and X minus, obviously, if I were to compare HX and HY, forming H plus and Y minus, if X minus is very stable, well then the equilibrium for the ionization of HX will lie far to the right. But if Y minus is very unstable, then the equilibrium for the ionization of HY will lie far to the left, because the stability of the proton is the same. So the stability of the counterion plays a significant role in terms of the acidity of the compound. I'm going to rephrase that. The stability of the conjugate base plays a very big role in the acidity of the compound. So in general, the more stable the conjugate base, the stronger the acid. And it has to be that way. If HX is a strong acid, it means we're going to go this way. What it must mean is that X minus is so stable a base that it's a weak base. Right? A stable species is one that's not reactive. And if a base is not reactive, it means it's a weak base. So a strong acid must be associated with a weak conjugate base. A weak conjugate base is another way of saying a stable conjugate base. And how did the base stabilize itself? By basically dissipating, not by basically, but by dissipating electron density. So we're going to come back to that idea next, that a strong acid must be associated with a stable or weak conjugate base. Okay.